Did I tell you that my dad found an entire box full of my college books? Including...
Is my Arfken and Weber and Harris in that?
It actually might have been. You loaned it to me ahead of Quantum, and then I just didn't take Quantum.
Yep. Well, you took it for exactly 3 days.
For like 3 days, I was like, I don't think so. Don't think I'm going to do this.
But you could have. Just think about it. Think how much more we could talk about my research if you had taken Quantum.
I couldn't. I didn't know bracket notation. How was I ever going to do Quantum?
You would have been. You would have learned. That's college. That's how that works.
I dropped it after they were like, using the uncertainty principle and this ice pick balancing, which way will it fall?
Oh, that was a great question. I forgot about that.
A terrible question.
No, that's a great question.
Welcome to the Reference Frames podcast, the physics podcast where Will and myself, Ian, take some of our favorite physics concepts and some of our favorite pop culture references, movies, TV shows, and likewise and otherwise, and try to combine them into one place where you, a listener, can listen, picture this sort of scene, and then understand a physics concept coming from there. My name is Ian. I take show running and ask Will to clarify when I'm confused by him. Will is the resident physics guy and is only 1 year away from a PhD if he's lucky.
If we're lucky.
Here we are. And always, of course, the first thing we do is take ourselves to the corrections corner. Oh, and what's that? Hello.
But soft.
Hello. No corrections in the corrections corner. Where are you people?
Yeah,
Go listen to the time dilation episode. It was number 3. I'm sure there are corrections.
Yeah, and I've never even seen Lawrence of Arabia, so I probably described that scene wrong. Come on,
folks. Tweet at us with your corrections. You can also email us, referenceframespodcast@gmail.com, with your corrections or questions, but we'll get to the questions later. And so since we have no corrections, we will instead transition swiftly and quickly into our scene. Will, please take the floor.
Isla Nublar, a beautiful island paradise off the Costa Rican coast, is soon to be the home of a state-of-the-art theme park boasting real live dinosaurs. After an unfortunate accident, investors ask a number of experts to visit the park and ensure its safety before opening to the public. As you would expect, this visit does not go well. The power of the park is shut off due to some corporate skullduggery, leading to T-Rexes and Velociraptors prowling around the park and eating a number of park personnel. Dr. Alan Grant, the visiting paleontologist, flees into the jungle with the grandchildren of the park's creator, Lex and Tim, and eventually make it to a large fence blocking their path back to the others. The fence is labeled with a large high voltage warning of 10,000 volts, but thankfully the power for the park is still down. Unbeknownst to Alan, Lex, and Tim, however, is that as they begin climbing over the fence, the other survivors are in the process of rebooting power back to the park to try and call for help. Alan and Lex make it to the far side, but Tim is still climbing down when the power is switched back on. Sparks fly as Tim is blasted back from the fence, but he is thankfully caught by Dr. Grant. CPR is performed, Tim regains consciousness, and the final act of the film begins, including a particularly terrifying encounter with the Velociraptors in the park's kitchen. Yeah, you knew it was coming. You knew we'd do Jurassic Park one day. Here it is.
Is he really just a paleontologist? He has to be more than that, right?
Well, I think Ellie, I forget, she's a paleobotanist, so they're kind of.
Well, he's just so talented. He does, he catches a kid. He does CPR.
Oh, he probably did some football back in high school.
He must have done something because he can drive a car good.
Everyone knows paleontologists were the jocks of high school.
Yeah, he's exceptionally fashionable.
Even with all that dust and grime over him, still looks
so good. He wears an ascot, I think.
Something like that. Scarf, maybe? I don't even remember.
It's something. It's
big hat. Nice big cowboy hat.
Oh, huge hat. Wow. I was so happy.
He's not quite as styling as Ian Malcolm, played by Jeff Goldblum.
That was my impression.
It's the laugh.
The laugh.
Anyway, Ian, what do you think the physics for the week is based on that scene?
It really sounded like we're focusing on that electric fence.
That is kind of the,
So are we going to talk maybe about, let's see here. I mean, there's such a whole world of electricity to talk about. Ohm's law is a nice basic one. We could go even easier with that. Are we going to talk about voltage and current and what they mean and how they work in the real life? Are we going to talk about the ability for an electric fence to launch a child? Are we going to talk about projectile motion of a child going through the air and then being caught miraculously? Oh my gosh.
You were a little closer to the mark on your first few guesses.
How much would that kid weigh?
Oh my gosh. What's his momentum? No, we are talking about a few things. So on the way to talking about voltage and current, we'll have to talk about charge as well. But those are the basic stuff we'll be talking about today. Kind of electricity, as you understand it, probably coming out of the wall socket.
Oh, exciting. I can't wait.
Yeah. So first, we should probably kick off by talking about what we mean by electric charge, right? So most people are probably familiar with the atomic model, right? There's protons and neutrons and electrons that orbit around the nucleus, right?
It's the Jimmy Neutron logo.
Exactly. The things that are moving are the electrons. And you just need to remember that the protons and electrons are positive and negative, respectively, right? And what that means is that the negatively charged electrons repel each other, and the positively charged protons repel each other, and the positive and negative charges attract each other. That's kind of the important bit. So just remember, electrons don't like to be near each other, and that's pretty much how we'll talk about all this fun stuff. So with that in mind, in a conductor, which is some material, so a lot of metals, or I think all metals fall into this, for certain atoms or certain elements, they serve as conductors in the right format. And what that means is that any electrons, or some of the electrons in that material that belong to those atoms, are able to move around away from their home atom, and basically can just move around freely wherever they want to go. And if there's more than one electron, they're free to move. They're going to get pushed away from each other, right? Because they repel each other. That's how charges work, right? And so that's kind of the important thing to know about these charges that can move around, these electrons. So batteries, right, as you're probably familiar with, like a 9-volt AA or a 12-volt battery or whatever like that, right? These things are useful because they're able to effectively pump electrons around. So they can pump electrons out of or into different metals or different conductive materials. And what that means is they can basically pump a bunch of electrons into a material and create a bunch of excess charge, a bunch of extra electrons that wouldn't be there normally. And what that means is that if you have another material, another object nearby that's conductive, that doesn't have a bunch of extra electrons in it, and you touch them to it, remember, these electrons want to get as far away from each other as possible. They want to get pushed as far as possible. And now, if this new one moves in, they can move freely through the conductor. They're going to get pushed into that other conductor by all the other electrons, right? They're basically going to try to spread out as far as possible. And look at that. They got free real estate. They want to move. And then they will move. They'll move to basically reorganize themselves to be as far away from each other as possible. And that includes moving into the new object. Does that make sense, Ian? How this all working?
That makes sense to me. And when we talk about a conductor, the most basic thing that everyone knows is wires. Wires are conductors. They're made out of metal. Electrons can traverse through them.
Yeah, exactly. And in fact, so you imagine I talked about touching these two objects directly. A lot of the times, instead of physically moving objects with different charges on them together, you'll connect them by something else, like a wire, right? And that'll basically act as the conduit that these electrons will get pushed through from all the other electrons.
Mm-hmm.
So this idea of having a bunch of excess electrons on one object and not on another object, that's where the idea of electric potential comes from. And that's what we think of when we talk about voltages, right? So let's say you have a bunch of excess electrons on object A, and you have a normal amount of electrons on object B. You would have an electric potential difference between the two of them because one of them has a lot of electrons and one of them doesn't. And that means if you connect them with a wire, you'll have a bunch of charges flowing, again, because they're getting pushed by all the other electrons around. They want to get spread out as far as possible, so they get pushed away into the other object. And that movement from one object to the other is what we call a current. That just means the charges are moving, they're being reorganized to be as far as away from each other as possible. Does that make sense?
Yeah, so when they're moving, there is a current. And at some point, they're like, okay, we're all as far away from each other as we can be. Now there is no longer current.
Yes, and there's no more potential difference, right? Because at that point, the two objects will have the same electric potential because they're the same amount of excess charges on both, because it will have equalized out. And it's also worth pointing out, I talked about putting excess electrons on an object, right? It also could work if you suck electrons out of one of the objects. In that case, right, one will have fewer electrons than normal, and the other object would have a normal amount. In this case, they'd move from the one that has a normal amount, because they'd want to move the area where there's fewer electrons because they're not pushing them as hard. So in that case, they would flow the opposite direction. The electrons would flow and equalize that way.
The more potential always wants to go towards less potential.
Exactly. Cool. And we talked about wires connecting to objects with different electric potentials, right? There's other things that could potentially connect to objects with different potentials. Perhaps a human body in this situation. So let's talk about the scene.
All right, let's talk about it.
So this scene is a somewhat simplified explanation I'm giving here. Actual electric fences that I think would make more sense for the situation aren't being used in the movie. And so we're going to talk about the ones that's in the movie, but then in the movie it doesn't quite work, and we'll talk about that at the end as well. So in this scene, we're told that the fence has a really high voltage, a 10,000 volt potential difference. It's not clear what that is between, if it's between the fence and the ground, or between individual fence wires or cables. Though, if you watch the scene back, you'll see there's a bunch of metal wires connecting all the cables like a mesh, so people can't squeeze through. So that would imply that they're all at the same potential. Because,
otherwise, they would not have to climb it. They could have just.
Well, yeah, that's actually part of the movie. Like, Dr. Grant tries to pull them apart to get through, but he can't, so they have to climb over it.
Yeah.
Anyway, so in this high voltage idea, though, there's a lot more electrons, or a lot fewer electrons in the fence than there are on the ground or whatever it's related to. And what that means for poor Tim, as he's climbing it, presumably when the fence gets turned on again by the unwitting Dr. Sadler, I think is her name, while Tim's holding on to it, presumably the cable he's holding on to has a heck of a lot fewer electrons or more electrons than the cable his feet are on, because as we can see, electricity basically is like, oh, the air I can't go through, but this kid, I can go through. So all the electrons get pushed through Tim, probably through his heart, because he loses consciousness and stops breathing briefly, blasts him off the back of the thing onto the ground.
Right.
And it's worth pointing out, electric currents, as you can probably imagine, can be pretty dangerous for humans, right?
Yeah.
But there's a reason for that, right? So muscles in general, and the heart in particular, rely on electrical phenomena to function properly. The heart requires a specific cadence of electric changes across parts of it to know how to beat in time. And so this is partly where defibrillators come from, right? It's all about shocking it. And if you have a huge amount of current going through it, that basically fries a lot of the electrical circuits in your body at the moment, which is why Tim has this near-death experience.
Right.
So basically the wires are using his body as a means of escape to the other wire.
As they're all climbing it, they're all at the same potential because the power's off, right? And whatever was, taking the electrons out of the fence is no longer running.
Yeah. Each wire has the same amount of electrons in every other wire.
Tim is climbing it. And all the wires are the same. So everything's got the same potential. They flip the switch. Two wires now have different potentials, different electrical potentials, which means one of them has fewer electrons than the other. And as we talked about, if you were to touch a wire between them, the electrons would run through. However, we have no wires here. Well,
we don't.
We do, but we don't.
There's a lot of wires, which is why it doesn't really work.
we ignore it for a little bit. But we do have a stand-in for a wire, which is a small child. Our conductor.
Exactly.
And so the electrons are going to move from one wire to the other.
Through him.
Creating a current.
Through his heart. Yes.
Not a great place for the current to be.
Not a great place. So that's the basic idea of this scene. We're basically seeing charges moving because there's too many charges in one area, not enough charges in the other, and the charges are getting repelled by each other, right? And so they're getting pushed through any way they can, in this case through a person, to an area where there's fewer charges pushing them away from it.
I mean, it's a little bit of movie magic, but...
I mean, the movie, like, the whole interconnected cables would work, in theory, if he was touching the ground and the cable. The fact that he's on the fence itself means it needs to be the alternating thing.
Which is sort of how birds can sit on a power cable, right?
Right, because it's just one potential value. They're not connecting two different cables with two different potentials.
Yeah.
All right, so Ian.
Yeah.
Now that we've talked about charges and voltages and currents, where in the world we don't see electricity, in the modern life, do we?
It's heat absorb. No, not at all. Boy, we see it all over the place. I mentioned birds, which is if you had a Timmy-sized bird who touched two of the power lines, you might have some issues. Of course, we also see the most obvious one is anytime you've been to a child's birthday party, there's absolutely guaranteed an adult taking a balloon and rubbing it on a child's head to mess up their hair and then to stick it to the kid.
Yeah, so what's going on there?
Well, the reason is the hair is being pulled towards the balloon because the balloon has more electrons or fewer. Really, in the end, it doesn't matter. It's all arbitrary.
Here's a real question, though. When you rub their head off with the balloon, their hair starts sticking to the balloon. You move the balloon away, and their hair still is standing up. And now it's kind of standing up just like all over the place.
All over.
Do you know why that's happening? It's really fun.
The electrons in the hair are trying to get away from each other.
Exactly right.
Oh,
or the lack of electrons. But we'll say the balloon rubbed a bunch of electrons off on the hair. Yeah, exactly right. We know electrons hate being near each other, so they'll move the hair itself if need be to get as far away from each other as possible.
What do you got?
Well, probably the most ancient and perhaps most deified version of lightning or version of electricity is lightning.
Oh, that was a bummer.
Yeah. Spoiler. So lightning, right? Lightning is a bunch of electrons zooming as fast as they can. And the way it works is actually not totally understood by scientists. Clouds are pretty complicated. But the basic gist is this. So when you have these big storm clouds, they're usually formed by having a bunch of hot air rushing up kind of through the center of it. Mm-hmm. And as that hot air is moving up, it's carrying a lot of lighter particles with it. So a lot of like water droplets and ice crystals and things like that up. And while it's moving up, all those particles moving up, there's also heavier particles, like little hail particles falling down because they're too heavy to be pushed up by the updraft. And as those particles run past each other, they're smashing and stealing electrons from each other. So you end up with a bunch of excess electrons on these heavier particles that are moving down, and then fewer electrons on the particles that are flying up. And so you end up with this kind of polarity built up across the top and bottom of the cloud. And in fact, the top you've probably seen a storm cloud. They often call them anvil tops because it kind of spreads out at the very top of it, sort of horizontally at the very top. So you end up with a big concentration of negative charge at the bottom of these storm clouds. And what that does to the ground underneath it, even though it's maybe a mile or whatever, I actually don't know how low the bottom of the storm clouds are.
Bold claim right there.
Whatever the height of a storm cloud is, that will actually push those excess electrons up there, will actually repel some electrons on the ground deeper into the ground. And so you end up with a net positive charge on the surface of the ground. And especially in any trees or like metal poles that are sticking up into the air. And so what happens, this is actually where it gets kind of complicated. So I don't fully understand it and I don't want to get too into it. But basically, these excess charges start creating what they call ion channels, which is basically they're stripping a bunch of electrons off or adding a bunch of electrons to air particles between the cloud and the, say, metal flagpole sticking up. And eventually, it creates a channel, basically a TIM in this situation, where all the excess electrons at the bottom of that cloud can now zoom to where they want to be, which is in that nice positive charged floor. So you get a huge torrent of electrons zooming through the air, which we see as lightning. Or any kind of spark, really. But lightning's the most spectacular.
Which connects back to the balloon, right?
Mm-hmm.
If you're outside in a thunderstorm and your hair starts to stand up, the air around you is becoming ionized, right?
Yeah.
The electrons are being moved around, and you are there's a higher chance that lightning is going to strike around you.
Yeah, which is
so
not a good thing.
Don't stand around and take a picture of yourself with your hair sticking up, because you can do that with a balloon. Maybe you get yourself to safety instead.
That means all your electrons are pouring into the ground away from you, and you don't want you don't want to get replenished by the sky. You want to get replenished by the ground. So don't wait around.
Yeah.
Yeah.
What's the solution again? You lay on the ground?
Yeah, get as low as possible.
There are a lot of different myths about how to survive a lightning strike. Some people say jump. Some people say stand on one foot.
I mean, technically, if you're really well insulated against the ground with big rubber boots on, maybe you'd be okay. But from what I understand, the best ideas are obviously get inside where you're not going to get zapped at all.
Yep.
Get as low as possible so you're not going to be the easiest point of access to the ground.
Because air is hard to zap through.
Air is hard to zap through. People are pretty easy, but metal poles are much easier.
So get below a metal pole.
Yeah,
but don't touch
not
it.
directly below it, but like
yeah. Also, don't stand under a tree. I've heard because they blow up.
They do.
What else you got? Or is that it?
I mean, that's the ones I want to talk about. I feel like we've talked enough.
Okay.
Unless you have anything else you'd like to talk about.
No, I think when it comes to electricity, we interact with it daily. Don't always really fully grasp the gravitas of electricity because a lot of what we do is handled by fancy pants electrical engineers that
Sure.
they spend their time blowing up little circuits inside their labs so that we don't experience little things blowing up. And so the ones we see mostly is like lightning and static electricity. And it's nice to know how they work.
Especially if you're worried about lightning. It's good to understand your fears.
Yeah, this podcast is now both physics and also how to survive a lightning strike.
Exactly. We provide really relevant advice to the world. All right. So I think that's
Awesome.
it, unless we have some questions.
We actually had a few questions come our way. We're not going to answer all of them today. So it goes. The first one harkens right back to, was it the episode before this one? Episode 4, Fermat's Principle. You can go check that out. It's all about Lawrence of Arabia and mirages.
Yeah.
The question comes from our friend at Anlon17. Is the pronunciation of homogeneous like tomato versus tomato? I always thought it was pronounced homogeneous. Homogenous, not homogeneous.
I think you mean. I don't think anyone says homogeneous. I hope they don't.
Oh, what a mistake. Wow,
unreal.
I should have practiced reading that better.
No, Ian just says tomato and just goes with it. Yes. That's just his go-to pronunciation.
And I double down on it. I always say tomato.
Anyway, great question. What was the at? Anlon?
Anlon17.
Anlon17. Great question, Anlon17. So this is actually a question I also had when I was in college, and my professors were all saying homogeneous all the time, and I had never heard that. I'd always heard homogeneous, like all the time, and a homogeneous mixture. So I Googled it back in college, and my little mind was blown because turns out homogeneous is the correct term for anytime anyone's saying homogeneous, they really mean homogeneous, unless they're a biologist from like 150 years ago, in which case homogeneous actually means something relevant. So from what I can tell from my research back in college and looking back up recently, homogeneous is the term for being evenly mixed. Homogeneous is a kind of somewhat archaic term now in biology that meant two things that had similar structure. So it was a synonym for homologous. So for example, a seal's flipper would be homologous or homogeneous to a person's arm, for example, which isn't usually what we mean when we say homogeneous nowadays. We mean homogeneous. So, with language being language, I mean, homogeneous has a new meaning, right? Homogeneous means homogeneous now, right? Because that's how language works. How people use it is how it means. So you're not incorrect for saying homogeneous, but technically, if you want to have a dictionary, you mean homogeneous whenever you're saying homogeneous.
Boom.
Hope that answers your question, Anlon17.
Thanks for the question. Question number 2, Will, comes from Facebook.
Oh.
Yes. So
Zuckerberg? He has one for us?
Zuckerberg has a question for us. We were tagged on a news.com.au video clip of what appears to be water standing still while flowing out of a pipe in midair. The quote says, "No, this water isn't frozen. It's just an insane and extremely rare phenomenon." As the water seems to be, stationary flowing out of this pipe, but a man brings his hand under and you can see it flows.
I see.
The question therein being, reference frames physics through pop culture. Help me understand.
Gotcha. Great question. So you're not seeing CG. Well, you might be, but it doesn't have to be CG. This could happen in real life, and I believe the video when they're saying not lying. I mean, what was it, news.uk?
.au.
Oh, AU, sorry. They would never lie. So what you're seeing there is a thing called laminar flow, which, me, I like my etymology. Laminar flow comes from the description of the actual phenomenon. So laminar flow is kind of the antithesis to turbulent flow, which you're probably very familiar with. Anytime you've seen eddies from a boat in a river, or really any kind of large body of water flowing, right? It's kind of chaotic, a lot of waves and whirls and things like that in it. That's called turbulent flow. And laminar flow is the exact opposite. So laminar flow means things are moving super smoothly and super cleanly. And how that actually works, how we model that, is we talk about these different layers of water basically sliding past each other, because you're always going to have water traveling at different speeds due to different constraints on the system. So in a pipe, for example, the water near the edge of the pipe will have to move slower because it's rubbing up against the edge of the pipe. The water in the middle of the pipe will be moving as fast as it possibly can, and it kind of has a gradient towards the edge. And the way you get laminar flow in that situation is the middle of the pipe water is moving faster, and then the water directly next to that, sort of concentrically outwards, is moving a little slower. Then outside of that, it's moving a little slower. So you get these basically different layers of water that are all moving at different speeds. And if they're sliding past each other, that's when you get laminar flow. If they're interacting and mixing, that's when you get turbulent flow. And so, etymologically speaking, it's interesting because lamina is Latin for a layer, so a small layer. So basically, laminar flow means layered flow, which is what we're seeing in that video and what we see whenever you have water flowing so smoothly as that. Hope that answers your question.
Bada boom. Will the
Bada
physics
boom.
man, 2 questions out of the park. Crushed it. Folks,
Foul ball, dang it.
Oh, all right, run it back. Folks, if you have any questions for us, they can be about science, they can be about pretty much anything, because we get a very limited number, so...
Yeah, I mean, etymology ones, and 117.
If you send a question, we'll likely answer it because we only get 3 a week.
If we got more, I would still answer them.
You can tweet at us at Podcast Frames is our Twitter username. You can find us on Facebook, Reference Frames Podcast. We just have a page. I don't really know how Facebook pages work, but you can find us there. You can even email us if you're really feeling like emailing us, or if you don't want to use social media, which is fine too. Our Gmail is referenceframespodcast@gmail.com. If you liked this episode, the best thing you can do to help us is sharing it with your friends and family and everyone in between. We don't pay for any advertising, because this is a passion project for us, which means, the outreach is based entirely on word of mouth. So we much appreciate everyone who has been doing such a thing. My grandma's our number 1 fan, I think.
Lois.
She's the best.
If you're listening to this right now, Lois, love you.
I think that's all there is to it. You got any parting words, Will?
Ian, you mentioned this email. We've really expanded our means of access. I think we should invest in a P.O. box. I think we should really get some actual mail. If you've gotten one piece of fan art, it's beautiful.
It's wonderful.
But some physical fan art would be even better.
Oh my gosh, that would be incredible. I'll see what I can do about securing a P.O. box.
Thanks, appreciate it. But I think that's all I got.
Thank you for listening, and we will see you next time.